video on continuity. So this is about the definition, which should look somewhat like the definition we had for the limit of a sequence. So again, we have a function. It's very important to always know what the domain of our function is. And so we say that a function f is continuous at some point a in its domain if, well, there's an epsilon and there's a delta. So we'll parse this through examples. So for every epsilon, there is some delta, such that if we take a point in the domain and the distance between that point x and our point a that we care about, then the distance between the two function values, right, f of our point a and f of this point x, then that's going to be smaller than epsilon. Okay? So I want to spend just most of this video going through examples talking about this, but the idea is if you want the outputs to be close together, in other words, suppose you let epsilon be 1/10, then that means at the end, you want to be able to guarantee that the difference between f of x and f of a, so the difference between those two outputs is going to be smaller than 1/10. Then you have to be able to show that there's going to be some condition on the inputs, right? If the inputs are within a certain distance of a, then they will lead to this condition. So let's just do an example. Suppose you knew that f of 2 was equal to 1, so that means the point 2, 1 is on the graph. Then we could just fill that information in. So f is continuous at the point a equals 2 if for every epsilon there exists a delta, such that if x minus a is less than delta, then f of x minus f of a is less than epsilon. So if we just fill in those values, then we'll get a 2 in for the a value and 1 because that's the value there. So that's one thing that we'll have to do that we didn't quite have to do with the limit definition. Notice here I've left out the if x is in the domain part. That probably will only come up very rarely. It's going to be okay if you forget that for the time being. Just remember, anytime you're plugging in a value x into a function, that point x needs to be in the domain. So really, it's sort of implicit since we're taking f of that point. And so just in practice, suppose we have a function, and suppose epsilon was 2, right? And suppose we wanted to show it was continuous at the point 2, then basically we want to say, well, can we choose some point x close enough to 2? So in other words, can we give a threshold delta so that if we're in that distance of 2, then the outputs are going to be within a distance of 2 outside of the thing, right? So I'm going to now switch over to this Desmos applet. And what we've got is we've got this really cool animation going right now. So maybe let me pause it. So this is the function f of x equals 3x minus 5. And you can see that's this diagonal line going up here. And in blue here, we have this threshold. So we've gone around the point 2, 1. And you can see at the moment this is called epsilon. And right now epsilon's set to be 0.5. So let me increase that up to 2. So now what we've got we've got a range of 2 in either direction from that output 1. And you can see, I've got different inputs, right? Suppose if I plug the number 4 into my function, I get way up here. So I won't be in that range. But of course, if I plug in a number pretty close to 2, I will lie in this blue range. And so what we have to do to prove that this function is continuous at the point 2 is we have to show that there's some safe range, that there's some interval around that number 2. So no matter what input we choose in there, we're going to definitely land in this blue strip. Right? And so let's see what happens, right? Suppose I went too far out, right? Suppose I got too far from the number 2. Suppose I went out even a distance of delta equals 1. Well, now I'm a distance 1 from 2, so that's the number 3. I come way up here, I'm outside of that blue strip. So if I were to give you a tolerance for your x values of 1, you might go too far out. I could be really safe and I could give you a delta tolerance of 0.1. It's over here somewhere. And then you'd have to be between 2.1 and 1.9, and your outputs would definitely be in that blue strip. And of course, what you imagine as it goes through, at some point we're okay, and at other points we aren't. And of course, if we change epsilon, let's make epsilon a lot smaller, let's make epsilon 1/2, well, what may have been good before might not be good anymore, because now we want to be within distance of 1/2, so our delta may have to be smaller. So I find this interactive applet really, really cool, because it lets you see exactly okay, we're red right now, that means we aren't in the appropriate range. Now we're blue, or now we're green, so that means that we're okay. And so just to give you an idea of these sorts of functions, maybe let's do another one. I wonder what would happen if I could do something like this. Let's just do something like x squared minus 2x plus 2. And let's again show that that's continuous at the point a equals 2. So we can zoom in maybe a little bit here. We can let our epsilon be 2. And let's see what our delta range can be. Let's make delta a little bit bigger. Let's see if we make it as big as 1. So yeah, you can see if we allow a delta range of 1, we're going to be okay on one side, but we're going to be not okay on the right. So if we go one step to the right, we could go all the way up to 3, and that'll get us outside of the blue range. But of course, intuitively, right, if we get close enough to 2, we're going to stay within that blue range. And as this is going, I can sort of decrease, try to erase it if I want. But I hope sort of what I've convinced you maybe is that no matter how small I make my epsilon, so epsilon is what I'm moving right now, that's the up and down. No matter how small I make this vertical range, if it's continuous, you can always get close enough in that horizontal range so that we stay within this strip. So in the next video, we're gonna use the delta and epsilon definitions to actually go through some of these proofs.